This week we're going to extend our discussion of oscillations and look at how we can use that type of mathematics to describe the motion of waves. So waves show up all over physics, whether you're talking about water waves or light waves or any kind of energy that propagates through a medium, sound waves, all sorts of things. And being able to describe the propagation of waves lets us do a lot in physics. So that's what we're going to talk about today. First of all, let me start by writing down our wave equation for a traveling wave. If you imagine you've got a wave that's, say you've got a rope or something like this and you pop a wave down it, that wave can travel in space, right? If I have the position here as a function of, the amplitude as a function of position, let's actually call this y. So how far the wave is displaced in the rope as a function of position, if I imagine I'm sitting here oscillating it, you'll see a wave go down like that. But it will also move in space, right? If you imagine, like a traveling wave, it's going to propagate down the medium in this way. So we actually have a two-dimensional wave. It's moving in both space and time. And so we need an equation that can describe that. The properties of waves are going to stay similar to what we've talked about before. We're going to have things like the wavelength, which is a description of the size of the wave in space. And we're going to have things like the frequency, which is a description of how quickly the wave is going by a certain point. So this is describing kind of the spatial motion, and this is describing the temporal motion. And we've already talked about the frequency being proportional to this thing called the angular frequency. So I can write down that the angular frequency is equal to 2 pi times the frequency. But we can do something similar with wavelength. We can say that a wave with a given wavelength has a wave number, which is kind of like a way of describing the size of the wave relative to each cycle, and we can say that variable is k, which is 2 pi divided by the wavelength. So this is the wave number. And if we do that, we can put both of those into a way of describing a sine wave traveling both space and time. And that is that the displacement as a function of space and time is equal to the amplitude times the sine of kx minus omega t. This is for a wave that's moving to the right. If it's moving to the left, it'd be plus omega t. And then we add on this phase constant, which just represents any shift for when the wave may have started. If we started the wave right here, but we could have started it at any point. And that is called the phase constant. So we can use this equation to describe this wave motion.